L to P is 3 kilometers. That's right. Okay. Great. And it makes 4 revolutions per minute. So 4 revolutions per minute. So this thing, okay, how fast is the beam of light moving along the shoreline when it is 1 kilometer from point P? So the light, you assume, can go as far as it needs to, okay? Especially since it's only kilometers away, not light years. Light travels pretty far. So it's saying right here, so we'll call this, I don't know, we'll call this point Q. So this is it's making the shoreline. So the thing is, theoretically, how far down the shore can this light shine? Theoretically, infinitely far, right? It's an interesting thing to think about, but the thing is, it's not a flat shoreline, right? It's going to curve a little bit. We're assuming that the shoreline is also straight, right?
So that's where my picture was entirely wrong.
So they're saying, what do they want? They want how fast is the beam of light moving along the shoreline? So we want what? D what dt? D dt of what?
QP.
QP, the magnitude of QP, that's right. We want d dt of QP when what? When QP is what? 1 kilometer, yeah. I was right, I'm sorry. Yep, 1 kilometer, great. Okay, so am I expecting you to write them at every single step? No. Clearly label what's going on. D theta dt is 8 pi radians per minute. Do you agree with that? Okay, so we haven't related anything yet, but we want, I'll highlight, yeah, we want this, correct? And we have d theta dt. So we want to relate theta and what?
Theta and QP.
Exactly. Good job. Theta and the magnitude of QP, right? Are we okay with that? Can we do that? I think we can. So theta is going to be right there. We know what LP is. What is LP?
3.
3, right? This degree, this is 90, right?
Mm-hmm.
So what is angle LQP? Nope. If this is 90 right here, thank you. We know it's 180 minus 90 minus theta, which is what? 90 minus theta. The point is we now have this, which is we know that this is 90 minus theta. That could prove to be helpful here. We need a relationship that relates theta and QP. What could we write? What trig function could we use? We know 3, and we have QP right here. There's QP. What? Someone said it. Tangent. We know that the tangent of 90 minus theta has to equal what? 3 over what?
1.
QP. QP is changing. It's at that specific state that we want to find the rate of change of QP, right? But QP, yes, is 1 at that specific point we want to examine, at that instant in time. So what does this tell us, though? This tells us that the magnitude of QP is equal to what? 3 over tangent of 90 minus theta. We have a relationship between the two. Do you agree with that?
Mm-hmm.
What's 1 over tangent? Cotangent. So what is this equal to? 3 cotangent of, do you agree with that?
Yep.
Okay, so we have a relationship between QP and theta. What do we do now?
Substitute.
No, so we don't need to substitute anything. That's the relationship we wanted, right? We differentiate both sides with respect to time. So what does the left become? D dt of QP. We have that. That's what we wanted, right? That's what we're trying to find. So D, I'm putting the parentheses so it's easier to see. This is 3 times, what's the derivative of cotangent, everybody? Negative cosecant squared times what? What's the derivative of cotangent? Is it just negative cosecant squared? So sad. I'm making a sad face right now, and I'm pausing it because I'm sad.
Because
Negative to begin with, right? Now, we don't have to isolate anything. We can now fill in the blanks with what for the state we're describing, right? So we know it's going to be d qp dt, which is what we want, equals 3 times, well, negative 3 cosecant squared of 90 minus, oh, we want the theta value at that specific instant times, oh, it's negative right here. So what does this become? Positive of, oh, what is d theta dt? 8 pi. We're missing, we want theta at qp equals what? 1. So we have a triangle here. It's 3, 1, and we want this theta value, right? The inverse tan of what? Of 3.
Isn't theta on top?
Oh, yes, I'm sorry. Yes. The theta for this.
Oh, yeah.
Ooh, we have to be careful. Hold on. This is important, everybody. Ooh, we just noticed something really, we have to be very careful here. This theta, we wrote it as 90 minus theta. This theta is still this theta right here.
Yeah.
So we need to make sure we take the right theta here. We want theta, and it's the upper one. It's this, that's where theta is, right? So this is 3 and this is 1. Tan inverse of 1/3. Thank you for catching. That's really important. Okay, so do we know, it's tan inverse 1/3 something we know the answer to?
No.
Well, if it was, what's the length of the hypotenuse on this thing? Root of what?
Root 10.
Root 10. If we made it 1, we'd have to divide everything by root 10. Does root 10 ever really pop out anywhere? No. So we know that d qp dt is equal to 3 times cosecant squared of 90 minus tan inverse of 1/3 times what? 8 pi. Can you guys do that out in your calculator? I'm going to do it out too, and we'll see if we can come to an agreement. And maybe it's what the book says too. Radians a minute. We did get that. They set this up here. You see this triangle right here? There's P. We know it's 3 from shore. So they just said, instead of, what did we call X here, this distance X? We called that what?
QP.
We called that Q to P, right? We called that Q to P. They set up a relation here where they set up X is equal to 3 tangent theta, which is exactly what we did. They took the derivative of both sides, and they wanted it when X equals 1 and tangent equals 1/3. The thing is that secant squared theta, blah, 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 I'm going to pause it for a second, is equal to what? It tells you it in the problem.
0.06.
Thank you. 0.06 radians a second. Got it. Find the rate at which the area of the triangle, so we want to relate what?
Area.
Area to what?
Theta.
To theta. Correct. There's a bunch of different ways to do this. What's one way we could do it? There's many different ways to find the area of a triangle. What's one way we could do the area of a triangle? 1/2 base times height, or what? There's an equation that uses sine, the 2 side lengths, and the included angle.
Oh.
1/2 AB sine theta. You remember that?
I do.
You can take that as a given. Okay, so if that's true, in this case, what are A and B?
4 and 5.
Yeah, so we know area is equal to 1/2 4 times 5 times
Sine theta.
sine theta. So area is going to be equal to 10 sine theta. Do you agree with that?
Yep.
So dA dt is going to be equal to 10 cosine theta times what? D theta dt. Do you agree with that?
Yeah. 10.
Okay, so dA dt, we want that when what? When theta is equal to what?
Pi over 3.
Pi over 3.
So 10 cosine
10
pi over 3,
cosine pi over 3 times
0.06.
0.06. What is cosine of 1? What is cosine of pi over 3? 1/2. So it's 10 times 1/2 times 6 over 100. This is how I just do it. So it's 5 times 6 over 100. So that's going to be 6 over 20, which is 3/10, which is 0.3. And do they give you a length meters or something in this? Yeah, they do. So this is the change in area. So what's the unit on this?
Meters.
Meters squared. It's area per second. Now here's the thing. This is the rate of change of the area when. So that's positive. So it's getting bigger at this point. It's getting bigger. Does that make sense? We good? Okay, I'll pause. Function x squared. Pretty sure we did. So we have this function x squared. We'll draw some axes here. So we have x and y. And here's our function x squared, just the positive side of it. So for example, There's the point 1, 1. Not drawn to scale, but there's the degree 1, 1 is through the function y equals x squared. That's nice, right? Could you find me the equation of that line of tangency at that point?
Yeah.
Sure. We need y prime, which is 2x. Y prime at 1 is 2. So the equation of the line of tangency there would be y minus 1 equals 2 times x minus 1. Do you agree with that? Where did we get this 2? This 2 was y prime evaluated at the x value, right? At the x value, let's call that x equals 1. That's y prime of 1. What was that value right there? Where did this 1 come from? That is the original function evaluated at 1. I'm mixing notation, so let's be consistent here. Instead of saying y prime, we could say f prime at 1. And this was the x value that we chose. Let's generalize this a little bit. So we know that point slope form is y minus y1 is equal to the slope times x minus x1. So let's say instead of saying x, let's generalize this to all functions and all x values. So let's say we want the tangent line at x equals a. Let's just say x equals a instead. So instead of saying y1, instead of saying x1, we would say a. What would we say instead of y1? F of a. So we have y minus f of a equals, and the slope is the derivative evaluated at f prime at times x minus a. So that represents the tangent line at an x value of a. If we draw that tangent line in, if we draw this tangent line in, and we only look at the neighborhood, the area close to x equals 1, what can you say about the tangent line when it's pretty close to 1?
It's very close to the curve.
It's pretty close to the curve. These are relative terms, right? Relative terms. Is it exactly on the curve? No, it's not exactly on the curve. So the question you're probably asking yourself is, what's the point? What's the point? The point is questions like this. Let's say I asked you this question. Find the linearization of the function x plus 3 at a equals 1. Let's just do that first, and then we'll see what we do with it. So what does that mean? It means find the tangent line of that function at a equals 1. So f of x in this case is the square root of x plus 3. What's f prime of x going to be, Chris?
That's going to be 1/2 times x plus 3
to the
negative 1/2.
Yeah, times 1. That's fine. I want you to say that. You're pumping out the chain rule. The chain rule always applies. It's 1 in this case. What's f prime at 1? 1/2 times 1 plus 3 to the negative 1/2, which is 1/2 4 to the negative 1/2. What's 4 to the negative 1/2? 1/2. So this thing is 1 over 4. So we know that the slope of the line is 1/4, and we want it at a equals 1. So we have the x value, so we need the, what's f of 1? It's the square root of 1 plus 3 is 2, principal root. So do we have our point? Yeah, 1 comma 1, 2, and our slope is 1/4. So y minus 2 is equal to x minus 1. So if I graphed y equals the square root of x plus 3 and I graph that line, where should they touch? What's the only point they should touch at? 1, 1. 1, 2, sorry, at 1, 2. So around the x value of 1, this is the linearization of that function. This is the linearization of that function. Do you agree with that right now? So how many different linearizations can you write? At a given point, there's only 1, right? But could you move, if I asked you for the linearization at a equals 2, is that a completely different line? Mm-hmm. Yeah, it's a completely different tangent line. So when you're asked for the local linearization, all they're asking you to find is the tangent line. That's it.
So it's sort of like derivative again.
Local linearization of f of x equals the square root of x plus 3 at x equals 1. That is the local linearization of f of x equals the square root of x plus 3 at x equals 1. How would we use this to approximate these values? If we wanted to know this value, the square root of 4.05, what would you do? If I just asked you right now, approximate that value without using any complicated math, what would you use?
Calculate.
Your calculator, you plug it in, right? We have a line that approximates the value of the square root of x plus 3 when x is equal to 1. So the further you get away from 1, it's less accurate, but it is an approximation. So let's actually draw a picture of what we're seeing here. The square root of x plus 3, where does that cross the x-axis? No. Negative 3. 1, 2, 3, right? And it goes like this. This right here is y equals the square root of x plus 3. And we just found the tangent line when x is equal to 1. Here's the tangent line right here. We found that equation. What was it? It was y minus 2 is equal to 1/4 of x minus 1. Does the slope look like it could be around 1/4 based on my pretty poor drawing? Yeah. So I want to use that line to approximate 3.98. What do I do? What do I plug in where? Okay, so let's look at the original equation here. If I wanted to find the square root of 3.98, what would x be here?
3.98.
0.98. Right? Be 0.98?
You put 0.98 and then you take the value of...
Exactly. So what are we going to do? We're going to take 0.98 and plug it in right there. So we have y minus 2 is equal to 1/4 times 0.98 minus 1. This is equal to 2 plus 1/4 of negative 1/50th, right? Agreed?
Yeah.
Y is equal to 2 plus, so 2 minus what? 2 minus 1 over what? 200.
Yeah.
So that's y is equal to 399 over 200. So we think the square root of 3.98 is approximately 399 over.
200.
Let's see if that logically flies. What's the square root of 4? 2. So the square root of 3.98 should be just a little bit less than. Is that a little bit less than 2? Yeah, let's test it out and see what it is actually. So if we actually do this on our calculator, the square root of 3.98, we end up with that. Is that pretty close? Well, let's see how close it is. We do this on our, that's what it is, but how could we ask our, we could do 399 divided by 200 minus what? What should I subtract from that? If I wanted to know how close they are together.
The answer.
Yeah, subtract that answer, right? We're going to subtract that answer. How close are we?
Really close.
We're really, really, really close. What does that mean when it says e negative 6?
The 10 to the negative.
Times 10 to the negative 6. So we are, ready? You take this and you move, how many times do you move the decimal place? Once?
6
Once,
times.
2, 3, 4, 5, 6, right? 0, 0, 0, 0, 0. How close are we?
Very.
Very close. Now here's the thing. Did we use our calculator to come up with this answer?
Nope.
No. We estimated the square root of 3.98 to how many decimal places? 5 decimal places with no calculator relatively quickly. Now what happens if I spread this out even further? Farther away?
It's going to get less accurate.
This right now can really help us estimate the square root of things around 4, right? Because when you plug in 1 into that, you get the square root, you're taking the square root of 4.
Yeah.
So 4.05, what do we plug into this?
1.05.
We plug in 1.05. We plugged in 0.98 before. How do we turn this into 4? 1.05. So if we do that out, we're going to end up with y minus 2 is equal to, am I recording here? Good. It's equal to 1/4 of 1.05 minus 1. Is this something we can do on our calculator? 2 plus 1/4 times 5 over 100. So it's y is equal to 2 plus 1 over what? 80, I think?
Yeah.
5, because it's 1/20th. 1/20th times 1/4 is 1/80th. So we end up with y is equal to 161 over 80. If we check this out on our calculator, 161 divided by 80, there's that. We're going to subtract from it the square root of 4.05. Is that better, or is that closer or farther away?
A little bit further.
It's a little further away. It's actually
It's further away from 4 than 3.9.
Yeah,
from 4. Exactly.
but it's still.
The curvature changes on either side, so it's not going to be a linear relationship in terms of the error rate. But in this case, it's
Still very different.
it's still pretty accurate, isn't it? 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. It's not quite, but it's still pretty good, right?
I guess it all depends on the equation too.
It's going to totally depend on the
Because
equation.
Some equations and some parts either
Yeah,
freaks
like
out
for
or it
example,
goes flat.
like what happens if I had an equation that was like, it was growing and then all of a sudden it spiked up like that, and I took the tangent line right here. If I took the tangent line right here, over to the right, the error would get really big faster than the error would get over here, right?
Yeah.
So it totally depends on the equation. But to summarize, when they ask you for the local linearization, what are you finding?
The-
Tangent line. And if they're asking you to approximate it, what was the hardest part, do you think, about doing this entire process? About answering that question. To you, what was the hardest part about answering that question?
You should find out
Do the math without the calculator.
Well, okay, two as you can. So do the reality
It's a
check.
little more straightforward.